Okay, hello everyone. I welcomes to all in our lecture series on superconductivity. In this lecture series, we are going to discuss these topics. Last class we have been discussed introduction to superconductivity. In this class, we are going to discuss Meissner's effect and mathematical explanation of Meissner's effect or validation of negative susceptibility, magnetic susceptibility or diamagnetism of superconductor in superconducting state. These topics are very much essential for B.sc, B.Tech, M.sc, M.Tech and various entrance examinations. Okay, so let us start today class. So in this class we are going to discuss Meissner's effect or behavior of superconductor in magnetic field. Last class we have been discussed above TC a superconductor shows its normal shows as a normal conductor. So above TC a superconductor shows normal conducting behavior. Below TC, below transition temperature, superconductor showing superconducting nature, or this is so called superconductivity of a superconductor, or you can say below TC called as your superconducting state. These things we have been discussed in our last class. Now we are going to consider two situations. This is one situation, situation 1, and this is your situation 2. Situation 2. In situation 1, suppose this is a superconductor which is at the temperature greater than that of the TC. That means in normal state. So for situation 1, superconductor is at normal state. In situation 2, superconductor is at temperature below TC. That means in superconducting state. Okay. Now we are going to apply magnetic field on both these situations. First we are going to apply magnetic field on this situation. First situation, that is your normal state. Whenever we are going to apply the magnetic field, all the magnetic flux are penetrates inside this superconductor. Magnetic field passed through or penetrate through the superconductor which is in normal state. But when magnetic field applied on a superconductor which is in the superconducting state, that means below TC, the magnetic fields are expelled or pushed outside from the superconductor. The word is expelled by superconductor in superconducting state. But in normal state, same magnetic field passed through the superconductor. But when the superconductor in superconducting state, then superconductor expelled the magnetic field. Okay, this effect is called as your Meissner's effect. So what is the definition? If one more question will be asked about Meissner's effect, what is Meissner's effect? That means in a superconductor in superconducting state expelled the magnetic field. This phenomenon is called as your Meissner's effect. That's it, you have to write. Okay, so here you can see a conductor which repels or expelled the magnetic flux outside applied magnetic flux. That means in superconducting state, this one, it behaves like as a diamagnetic diamagnetic. That means which is repelled, which can repel the applied magnetic field. So according, we know that a diamagnetic magnetic material having the susceptibility is negative. Here also I have been written. That means susceptibility negative means it will repel. Its characteristics is your repelling the applied magnetic field. So here from this Meissner's effect, it can be concluded that the perfect the superconductor which is in the superconducting state showing a perfect diamagnetic nature. Same thing I have been written according to Meissner. According to Meissner, what at superconducting state a superconductor shows perfectly diamagnetic nature or magnetic susceptibility is negative. Okay, so this is all about your Meissner's effect. Now here you can see that this black color is a superconductor which is inside the liquid nitrogen. this is a liquid nitrogen. So hence this is in the superconducting state. This is superconductor is in the superconducting state, because liquid nitrogen temperature around mm, minus minus 190 minus 190 degree centigrade around. So if this is a superconductor, suppose YbCO, so this superconductor is in the superconducting state. So if we have to put a tiny magnet over this, then this superconductor will repel the applied magnetic field, or it will repel the this magnet. Okay, or you can say expel the magnetic field lines which will be executed by this tiny magnet. So if I am going to put this magnet which has some, suppose, magnetic field lines like this, these lines will be repelled or expelled by this superconductor, due to which it seems to be float on the superconductor. With this technology, uh, or this technology called as the levitation technology, it is a small video you can see over here. uh, Here you can see this is liquid nitrogen. Okay, we have to just put, this is the YbCO superconductor. Liquid nitrogen I told us around 196 degree centigrade. So this YbCO superconductor will be in the superconducting state. So whenever we have to put on the magnet, it will be float, or it will be repelled by these magnets, and it will float over these magnets. So this is called as your levitation technology. Or with the help of this technology, we can imagine the levitation at train technology. Okay, and the mechanism is your quantum levitation. This is also called as the quantum levitation or quantum draft. Okay, okay, now we are going to go for validation of negative magnetic susceptibility, or the so-called mathematical explanation of Meissner's effect. Okay, here this is the explanation. We know that in general B equal to mu h. This is your permeability of a material, which is nothing but permeability of free space into relative permeability, mu naught into mu r into h. B equal to mu naught mu r, we know that 1 plus susceptibility. Okay, 1 plus susceptibility, here magnetic susceptibility J m into h. And here we discuss that in case of Meissner's effect, there is no magnetic flux inside the superconductor. All are expelled by the superconductor. So inside the superconductor, in superconducting state, magnetic lines are zero, or we can say B is your zero. Same thing we have been uh, considered over here. So in superconducting state, I have to write over here. In case of superconducting state, in case of superconducting state, B value is 0. I substituted instead of B equal to 0. So this value will be equal to 0. That means 1 plus Jm will be equal to 0. That implies Jm equal to minus 1. Here we found negative susceptibility or magnetic susceptibility, which represents the characteristic of dimagnetism. Okay, okay. Now we are going to consider Ohm's law. According to Ohm's law, we know that V equal to IR. V is the voltage, applied voltage, I is the current, this is the resistance. And electric field is nothing but potential difference. This, suppose this is the conductor. So uh, at the two end, the potential difference is V. And this is the length, suppose L. So electric field induced inside this conductor is equal to potential difference by this length, V by L, right? Suppose this conductor length is L and area is your A, right? That implies E can be written as, instead of V we can write IR by L. Okay, and I, instead of I we can write JA, because we know that current density is J is the current density, right? I by A, current per unit area. So instead of I, we can write J into A into R by L, and this will be equal to rho into J. Here rho is nothing but your resistivity of a conductor. How? Here you can see, we know that the resistance is proportional to the length and inversely proportional to the area, or resistance is nothing but resistivity, some constant, that is resistivity, into L by A. So that implies resistivity will be equal to Ra by L. So instead of this one Ra by L, we can write resistivity into J. At superconducting state, we know that the resistivity will be supposed to be 0. So if we have to substitute this value 0, then E equal to 0. Now consider the third Maxwell's equation, electromagnetic Maxwell's third equation, that is del cross E equal to minus del P by del T. So if E is 0, then del B by del T, the rate of change of magnetic lines, will be equal to 0. That means B equal to constant. B will be, that means from this derivation, if I am going to consider the electric resistivity and its derivation, we found magnetic lines is constant in the superconducting state. But in this way we found negative susceptibility. That means there is no magnetic flux inside the superconductor in the superconducting state. But here, by considering the uh, electric explanation, electromagnetic explanation, we found B equal to constant. Magnetic field inside the uh, superconductor in superconducting state is a constant. So from these two results, what we found, I written, this represents the magnetic flux, same thing I written, inside the superconductor below Tc or in superconducting state is constant, does not change. This is the contradiction to Meissner effect. Meissner told that in superconducting state, superconductor shows a negative susceptibility, that means it will expel all the magnetic flux. But if I am going to consider Maxwell's equation, it told that magnetic field is constant. Both are contradicted with each other. So here zero resistivity, that means electric way, if I am going to consider, that is your so-called zero resistivity, and perfect diamagnetism or Meissner's effect, both are mutual independent with each other, right? So finally it is concluded that superconductivity is not only a diamagnetism but a new type of diamagnetism. This new type of diamagnetism is explained by London brothers, or London equation came to explain this uh, new type of diamagnetism, okay, by London brothers. The famous equation called as London's equation. Then after BCS theory came to explain the superconductivity. So here I am going to stop this lecture, today's lecture. In next lecture or video, we are going to discuss London's equation, which explains the superconductivity or both zero resistivity and perfect diamagnetism, or the so-called new type of diamagnetism. So thank you so much for watching this video. Thank you.